Alrighty. 1 second, y'all. We'll get this started. I'm gonna do my Streamlabs. Streamlabs. Cool. Streamlabs. Nana Coffee. Yo, what's going on? Yo. All right, sweet. All right, cool. Give me 1 second, and we'll get this show started. I was muted. All right, here we go. We're back. All right, everybody. Hello, welcome back in. I hope you're having a wonderful day. Welcome back into the stream. Today is Saturday, September 13th, 2025. Let me know what you guys are working on and welcome back in. Today is going to be a good day as we jump in and read section 4.4 from Introduction to Algorithms, CLRS. This is going to be let's see how many pages this one. This starts on 95 and goes until 101. Okay, so maybe we'll read 4.4 and 4.5. That's probably, yeah, that's a good 4.4 and 4.5. We'll probably leave it off on 4.6. And then we will come back, 4.6 and 4.7 probably in one stream. And then that will finish off the chapter. Sweet, so 2 more streams and we'll be done, including this one. So 1 more after this, and we'll be done with chapter 4 here, moving on to chapter 5. Chapter 4 is honestly is a little bit more of a difficult chapter. It's really ramped it up quite heavily here regarding just like what it's teaching and kind of applications here. So we definitely need to go back through some of these previous chapters and get a little bit more practice with the problems and whatnot. Hey Wesley, how's it going? Hope you have a great day. Algorithm on. Thanks so much, Wesley. What you been working on? Appreciate you so much for coming in here, my dude. Mohammed, what's good, Mohammed? You are the man, Mohammed. We've got some cool new alerts on this on the channel here. If you sub and whatnot, it'll throw an alert on the screen. So awesome if you guys are interested in that. You guys can get your name shown up on the screen. Feel free to sub, follow along, however you feel. Okay. All right, let's get into today's stream. We'll start the Twitch here too. Okay. Let's start recording. All right, welcome back in, everybody. My name's Michael. Hope you're having a wonderful day so far. Today we're going to be jumping back into Introductions to Algorithms, Chapter 4. This is the 4th edition by CLRS. We're going to be jumping... Sorry, let me restart that. All right, hello, everybody. My name is Michael. Thanks so much for joining me, and welcome back into the channel. Today we're going to be jumping back into Introductions to Algorithms by CLRS, 4th edition, more specifically Chapter 4.4, the recursion tree method for solving recurrences, and Chapter 4.5. We're going to be reading these two sections today, and it should be a good little study session. I potentially will probably hop back on later this evening for a little bit of work on our MIT 6.0002 Introduction to Computational Thinking and Data Science problem set 3 work. We are currently on week 8 or problem set 3. Almost done with this problem set to then work and move on to watching the week 9 lecture. So really kind of on the back end of that course, just kind of things are getting a little bit more lengthy in terms of their homework assignments and the problem set, so that's why it's taking a little bit longer. But that's beside the point. Today is about Introduction to Algorithms by CLRS. We're going to be jumping back into 4.4, the recursion tree method for solving recurrences. Let's go ahead and get started. What's going on, Mr. Tim? Okay. I'm going to go slow and steady. We're going to read through this, hopefully little errors, and we'll be chilling. All right. Although you can, 4.4, the recursion tree method for solving recurrences. Although you can use the substitution method to prove that a solution to a recurrence is correct, you might have trouble coming up with a good guess. Drawing out a recursion tree, as we did in our analysis of the merge sort recurrence in section 2.3.2, can help. In a recursion tree, each node represents the cost of a single subproblem somewhere in the set of recursive function invocations. You typically sum the costs within each level of the tree to obtain the per-level costs, and then you sum all of the per-level costs to determine the total cost of all levels of the recursion. Sometimes, however, adding up the total cost takes more creativity. A recursion tree is best used to generate intuition for a good guess, which you can then verify by the substitution method. If you are meticulous when drawing out a recursion tree and summing the costs, however, you can use a recursion tree as a direct proof of a solution to a recurrence. But if you use it only to generate a good guess, you can often tolerate a small amount of sloppiness, which we can simplify the math. When you verify your guess with the substitution method later on, your math should be precise. This section demonstrates how you can use recursion trees to solve recurrences, generate good guesses, and gain intuition for recurrences. Hey Austin, how's it going? Welcome back in. It's awesome to hear from you again. How you doing, my friend? Nana Kofi's, I'm on CS50 Web right now. How did you get so good at web scraping? I'm blushing. I don't think I'm good at all. I honestly, that was my first time ever doing it. I just, the playwright in Python made it really easy just to do that. The methods and whatnot made it really easy to go over. All I had to do was just look up a couple of methods within it to get the window open. And then once I, learned how to actually, get the information to actually access the HTML, I just pretty much accessed the elements within, but then I refactored that code down to just actually intersecting the network responses that were given. So I'm kind of just tapping into the API responses that are given, that are public facing. So yeah, it wasn't like I'm actually scraping. I originally was scraping the HTML and waiting for things to load and doing it that way, but I refactored that down to actually just extract out the data package sent, and kind of be the middleman and just wait in the middle and catch it, if that makes any sense. But I don't think we're any. That's the first time we've ever done it, and yeah, it worked out kind of successful. But yeah, we definitely got a lot more to learn too. How's your CS50 going? How's CS50 web? All right, an illustrative example. Let's see how a recursion tree can provide a good guess for an upper bound solution to the recurrence of t of n equals to 3t of n over 4 plus theta n squared, right? Figure 4.1 shows how to derive the recursion tree for t of n equals to 3t n over 4 plus cn squared, where the constant c is greater than 0, is the upper bound constant in the theta n squared term. Part A of the figure shows t of n, which part B expands into an equivalent tree representing the recurrence. The cn squared term at the root represents the cost at the top level of the recursion, and the three subtrees of the root represents the costs incurred by the subproblems of size n over 4. Part C shows the process carried one step further by expanding each node with cost t of n over 4 from part B. The cost for each of the three children of the root is c of n over 4 squared. We continue expanding each node in the tree by breaking it into its constituent parts as determined by the recurrence. Because problem sizes decrease by a factor of 4 every time we go down by one level, the recursion must eventually bottom out in a base case where n is less than n naught. By convention, the base case is t of n equals to theta of 1, where n is less than n naught, and where n naught is greater than 0. Is any threshold constant sufficiently large that a recurrence is well defined? For the purpose of intuition, however, let's simplify the math a little. Let's assume that n is an exact power of 4, and the base case is t of 1 equals to theta of 1. As it turns out, these assumptions don't reflect the asymptotic solution. What's the height of the recursion tree? The subproblem size for a node at depth I is n over 4 to the power of I. As we descend the tree from the root, the subproblem size hits a n equals 1 when n over 4 to the power of I equals to 1, or equivalently when I equals to log base 4 of n. Thus, the tree has internal nodes of depths 0, 1, 2, all the way up to log base 4 n minus 1, and leaves at depth log base 4 of n. Part D of figure 4.1 shows the cost at each level of the tree. Each level has 3 times as many nodes as the level above, and so the number of nodes at each depth is I is 3 to the power of I. Because subproblem size is reduced a factor of 4 for each level further from the root, each internal node at depth I equals to 0. Each internal node at depth I equals to 0, 1, 2, all the way to log base 4 n minus 1 has a cost of c times n over 4 to the power of I squared. Multiplying, we see the total cost of all nodes at a given depth I is equal to c to the power 3 to the power of I times c of n over 4 to the power of I squared, which equals to c 3 over 16 to the power of I times c n squared. The bottom level at depth log base 4n contains 3 to the power of log base 4n, which equals to n log base 4 times 3. Leaves using equation 3.21 on page 66. Each leaf contributes theta of 1, leading to a total leaf cost of theta n log 4. Oh my gosh. Okay, I'm going to restart this sentence here. Multiplying, we see the total cost of all nodes at a given depth I is 3 to the power of I times c of n over 4 to the power of I squared. which reduces down to 3 over 16 to the power of I times C times n squared. The bottom level, at depth log base 4 times n, contains 3 to the power of log base 4 times n, which equals to n to the power of log base 4 times 3, leaves using equation 3.21 on page 66. Each leaf contributes theta of 1, leading to a total leaf cost of theta of n log base 4 times 3. We add up the costs over all the levels to determine the cost of the entire tree. So this reduces down to O of n squared. We've derived the guess of T of n equals to O of n squared for the original recurrence. In this example, the coefficients of C times n squared form a decreasing geometric series. By equation A dot 7, the sum of these coefficients is bounded from above by the constant 16 over 13, since the root's contribution to the total cost is Cn squared. The cost of the root dominates the total cost of the tree. In fact, if On squared is indeed an upper bound for the recurrence, as we'll verify in a moment, then it must be a tight bound. Why? The first recursive call contributes a cost of theta n squared, and so omega n squared must be a lower bound for the recurrence. Let's now use the substitution method to verify that our guess is correct, namely that T of n is equal to big O of n squared is an upper bound for the recurrence. T of n equals to 3t n over 4 plus theta n squared. We want to show that T of n, which is less than or equal to d times n squared for some constant d, which is greater than 0. Using the same constant c greater than 0 as before, we have this, where we prove that T of n is less than or equal to d times n squared. Or the last steps holds if we choose d of greater than or equal to 16 over 13 times c. For the base case of the induction, let n not be greater than 0, be a sufficiently large threshold constant that the recurrence is well defined when T of n is equal to theta of 1 for n less than n naught. We can pick d large enough that d dominates the constant hidden by the theta, in which case d n squared is greater than or equal to d, which is greater than or equal to theta of n, for 1, which is less than or equal to n, which is less than n naught, completing the proof of the base case. The substitution proof we just saw involves two named constants, c and d. We named c and used it to stand for the upper bound constant hidden and guaranteed to exist by the theta notation. We cannot pick c arbitrarily, it's given to us, although for any such c, any constant c prime which is greater than c or equal to c also suffices. We also named d, but we were free to choose any value for it that fit our needs. In this example, the value of d happened to depend on the value of c, which is fine, since d is a constant if c is a constant. Lots of info there. Hey, Stormy, how's it going? Has your current major then subsequent job allowed you to live a comfortable life? Is there a reason beyond climbing the career ladder to learn programming or discipline is inspiring feat? That's a good question. And yeah, so we kind of talked about this a little bit in my last stream, but the biotech industry is fairly slow. The kind of career paths that you're forced to take, kind of all roads lead to middle management. Like at least from the current field I'm in and the current company I'm with, all roads seem to kind of lead down towards just middle management and removing yourself from laboratory work, removing yourself from doing actual product contribution and customer facing interactions of what you're doing. So it's not really like it just kind of, I don't know, that as well as wanting to gain new skills. I felt that I was like just every day after school, after college, since being done and graduated after work, I just was forgetting more and more material from school and kind of like losing sharpness in becoming, or just my studying and whatnot. So I was also feeling bad that I was giving up all of that work I had done in the past, and I didn't want to have to go back through and like review chemistry because I honestly don't really have a desire to go any further in chemistry and biology. I don't really want to go for like a master's or doctorate in that field. If I was going to go back, it would be for probably computer science. But I thought, I might as well. I've always thought this was interesting. Let's learn, and here we are. So yeah, that's pretty much the gist of it. Nice. That's awesome, Nana Kofi. Okay, so I'm gonna take this, and I'm going to get some more info here. Break this down. You passed a big chunk from CLRS intro about analyzing the recurrence. Let's carefully break this down. The recurrence, we're analyzing divide and conquer, where each problem of size n splits into 3 subproblems. Each subproblem is size n divided by 4, plus a combined cost of theta n squared. So formally, the recurrence is this. Recursion tree idea. We expand the recurrence as a tree. Root, the problem size of n, which costs c of n squared. Level 1, 3 subproblems, each of n over 4, which cost, c of n over 4 squared, right? Which is c of n over 16, c of n squared over 16. Level 2, each of the subproblems splits into 3, so there are 3 squared nodes of size n over 4 squared, each costing c n over 16 squared. Height of the tree. At depth I, subproblem size n over 4 to the power of I, base case, when n is over 4 to the power of I is equal to 1, we solve I, so the recursion tree has this height of log base 4 equals to n. Cost at the level I. Number of nodes is 3 to the power of I. Cost per node is c times n over 4 to the power of I squared, which equals to this. So the level cost is here. So the leaf cost grows at this rate, and the total cost of the tree is the sum over across of all the internal levels. Okay. So let's kind of go over this figure here. So we have our original tree here, which is bounded by that larger factor here of the n squared, right, at its root. We divide each subproblem, 3 subproblems, into n over 4. So 3 subproblems are created, each of size n over 4. And then here, we insert this recurrence into our equation for the bound of this recurrence, right, step. So we plug that in for n here, n over 4 squared, and so on and so forth. Interesting. It's going great. Done with searching. Okay, nice. Yep, here, yeah. I'm always shadowing these streams, and I've been inspired to learn programming as well as want to make a game one day. Nice, Stromy. That's really cool. What kind of game you want to make? I'm kind of lost, to be honest. I don't know whether or not I should get my CS degree. Honestly, don't have the money to pay each semester. Yeah, that's tough for sure. The financials are always, yeah, that's honestly not a reason too why I'm not going back, is that I don't really want to pay for something that's not really like a guarantee anymore. Is in the past, you kind of traded the monetary value for the guarantee that you would kind of be able to find work with the certification of the bachelor's in computer science. But That's just not really the case anymore. So there is more of a risk to the investment, right? There is more risk to reward than there is reward to risk at the moment than previous years. So let me ask, what is this trying to teach us? Can you break it down? Okay, here's the lesson flow in simpler words. We're learning how to solve recurrences. Divide and conquer algorithms are often expressed as recurrences like this, where we have some variables are now plugged in. Okay, this shows up in many algorithms, sorting, matrix multiplication, etc. The recursion tree is a visual tool, right? Each level of the tree equals one round of recursive calls. At each level, you see how many subproblems you have, how big each subproblem is, and what their cost is. This lets you add up the total cost across all levels. Geometric series intuition. Cost at deeper levels shrink by a fixed ratio. Here, 3 over 16. That's a geometric series. The total sum of a geometric series is bounded by a constant multiple of the first term. So the root cost dominates, right? The leaves matter too. At the bottom, you have some number of constant size problems. Sometimes the leaves dominate, sometimes the roots dominate. In this case, the leaves take theta of n to the power of 0.79, which is much smaller than the root of theta n squared. Verifying with substitution. After guessing theta of n squared, you prove it rigorously by induction. So what's this teaching you? How to systematically analyze divide and conquer algorithms. The process, write the recurrence, expand the recursion tree, look at cost per level, decide whether the root, leaves, or all levels dominate, and prove the substitution. So big takeaways, this example shows you how the recurrence tree method gives intuition, root dominates, and how the substitution method formally proves it. It's training you to recognize growth patterns in recurrences. Cool. Okay, an irregular example. Let's find an asymptotic upper bound for another more irregular example. Figure 4.2 shows the recurrence tree for the recurrence of t of n, which is equal to t of n over 3 plus t of 2n over 3 plus theta n. This recursion tree is unbalanced, with different root to leaf paths having different lengths. Going left at any node produces a subproblem of 1/3 of the size, and going right produces a subproblem of 2/3 the size. Let n naught be greater than 0 be implicit threshold constant that t of n is equal to theta of 1 for 0, which is less than n, which is less than n naught. And let c represent the upper bound constant hidden by the theta n term for n greater than or equal to n naught. There are actually two n naught constants here. One for the threshold in the recurrence, and the other for the threshold in the theta notation. So we'll let n naught be the larger of the two constants. Gotcha. Okay, so we start off with some bound of c of n, right? We divide each left-hand subproblem into n over 3, and we divide the right-hand subproblem in a recursive 2n over 3. Each of these has a cn total running time bound, right? Yeah, because these are just constants being applied. The height of the tree runs down the right edge of the tree, corresponding to the subproblems of size n, 2 over 3n, 4 over 9n, all the way up to theta of 1, with cost bounded by c of n. C 2n over 3, C 4n over 9, up to theta of 1, respectively. We hit the rightmost leaf when 2 over 3 to the power of h, n is less than n naught, which is less than or equal to 2 over 3 h minus 1 n, which happens when h is equal to the floor value of log base 3 over 2 of n over n naught plus 1. Since applying the floor bounds in equation 3.2 on page 64 with x equals to log base 3 over 2, since applying the floor bounds in equation 3.2 on page 64 with x equals to log base 3 over 2 of n over n naught, we have 2 over 3 to the power of h times n equals to all of this. I'm not going to read this out. Thus, the height of the tree is h equals to theta log n. We are now in a position to understand the upper bound. Let's postpone dealing with leaves for a moment, summing the cost of internal nodes across each level. We have at most Cn per level times the theta log n tree height for a total cost of big O of n log n for all internal nodes. It remains to deal with the leaves of all the recursion tree, which represent base cases, each costing theta of 1. How many leaves are there? It's tempting to upper bound their number by the number of leaves in a complete binary tree of height equals to h of the floor log base 3 over 2 of n over n naught plus 1, since the recursion tree is contained within such a complete binary tree. But this approach turns out to give us a poor bound. The complete binary tree has one node at the root, two nodes at depth 1, and generally 2 to the power of k nodes at depth k. Since the height is equal to the floor of log base 3 over 2 n plus 1, there are this many leaves in the complete binary tree, which is an upper bound of the number of leaves in the recursion tree. Because the cost of each leaf is theta of 1, this analysis says that the total cost of all leaves in the recursion tree is big O n to the power of log base 3 over 2 squared, which is equal to n to the power of 1.71, or big O of n to the power of 1.71, which is an asymptotically greater bound than the big O of n log n cost of all internal nodes. In fact, as we're about to see, this bound is not tight. The cost of all leaves in the recursion tree is big O of n asymptotically less than big O of n log n. In other words, the cost of all the internal nodes dominates the cost of the leaves, not vice versa. Rather than analyzing the leaves, we could quit right now and prove by substitution that T of n is equal to theta of n log n. This approach works, see exercise 4.4-3, but it's instructive to understand how many leaves this recursion tree has. You may see recurrences for which the cost of leaves dominate the cost of internal nodes, and then you'll be in better shape if you've had some experience analyzing the number of leaves. To figure out how many leaves there are, let's write a recurrence L of n for the number of leaves in the recursion tree for T of n. Since all the leaves in T of n belong either to the left subtree or the right subtree of the root, we have this, L of n, which is equal to 1 if n is less than n naught, or L of n over 3 plus L of 2n over 3 if n is greater than or equal to n naught. This recurrence is similar to recurrence 4.14, but it's missing the theta of n term, and it contains an explicit base case. Because this recurrence omits the theta n term, it is much easier to solve. Let's apply the substitution method to solve that. It has a solution of L of n equals to big O of n. Using the inductive hypothesis, L of n less than or equal to d of n for some constant d greater than 0, and assuming that the inductive hypothesis holds for all values less than n, we have L of n, which is equal to L of n over 3 plus L of 2n over 3, which is less than or equal to d times n over 3 plus 2 times d times n over 3, which is less than or equal to d times n, which holds for any d greater than 0. We can now choose d large enough to handle the base case ln equals to 1 for 0, which is less than n, which is less than n naught, for which d is equal to 1 suffices, thereby completing the substitution method for the upper bound on leaves. Exercise 4.4-2 asks you to prove that L of n equals to theta of n. Returning the recurrence 4.14 for T of n it now becomes apparent that the total cost of leaves over all levels must be L of n times theta of 1, which is equal to theta of n. Since we have derived the bound of big O n log n on the cost of the internal nodes, it follows that the solution to recurrence 4.14 is T of n equals to big O of n log n plus theta n, which is equal to big O of n log n. Exercise 4.4-3 asks you to prove that T of n equals to theta n log n. It's wise to verify any bound obtained with the recursion tree by using the substitution method, especially if you've made simplifying assumptions. But another strategy altogether is to use more powerful mathematics, typically in the form of the master method in the next section, which unfortunately doesn't apply to recurrence 4.14, or the Acrobasi method, which does but requires calculus. Even if you use a powerful method, a recursion tree can improve your intuition for what's going on beneath the heavy. Even if you use a powerful method, a recursion tree can improve your intuition for what's going on beneath the heavy math. Interesting. That was a lot as well. So let's get a little breakdown of this guy here. So let's take this guy here. Let's get a breakdown. You grab another example from CLRS. A different recurrence than before, namely this. That's a common two-way split recurrence where one subproblem of size n over 3 subproblem and one subproblem of size 2n over 3 and linear work to combine. Let's unpack this section, what this section is teaching you. What the recurrence tree looks like. The root has cost of Cn. Its children, left side, has size n over 3, which is cost equal to C times n over 3, and the right child has size of 2n over 3, which is cost of about C times 2n over 3. Then keep splitting recursively. The right edge of the tree, always choosing the larger 2n over 3 branch, defines the height. Height of the recursion tree. At each step, the right branch shrinks by a factor of 2/3. After h steps, size equals to 2/3 to the power of h times n. This bottoms out at the base case when size is less than n naught. And we solve that by saying that 2/3 to the power of h times n is less than n naught, which equals to h equaling big theta log base 3 over 2 times n over n naught. So the tree's height is big O of log n. Cost of internal nodes. At each level, the total cost of all nodes is bounded by C times n. Level 0 is n, level 1 is n over 3 plus C times n over 3 plus C times 2n over 3, which is Cn. It still adds up to Cn, and so on. So there are big O of log n levels. The internal node costs big O of n log n. What about the leaves? Leaves equals the base case where the subproblem size is less than n naught. Each leaf costs theta of 1. So the naive bound, a complete binary tree of height O of log n would have about 2 to the power of log n, which equals to about n to the power of 1.71 leaves. That suggests a leaf cost of big O of n to the power of 171. But this is an overestimate because our tree is not perfectly balanced. The right subproblem is bigger than the left subproblem. They set up a recurrence for the number of leaves, L of n equals to, right, those recurrences summed together, those left and right recurrences. And by induction, we prove that the total leaf cost is big O of n. We combine everything, so big O n log n, the leaves, O of n, so the total is big O of n log n. And with the substitution method, you can tighten it to big theta of n log n. So what's the point of this example? It's teaching you, don't just assume the leaves dominate. Sometimes they don't. How to carefully count leaves using a separate recurrence. And that even messy, uneven splits, n over 3 and 2n over 3, the total per level can still always be neat of big O of n. And to always check the substitution to be sure. the bigger lesson. This example contrasts with the earlier one where the root dominated. Here, the cost per level is balanced and the sum of all level internal nodes dominates. So, depending on the recurrence, different parts of the tree may dominate the total cost. Okay, that helped a lot too. Let me catch up on some chats here. Thanks so much for hi Doman. I appreciate you for coming in again. It's great to hear from you. Knowledge is infinite. Whether you decide to stay in the industry, it doesn't matter. Go into anything you want to, and don't let artificial value strip you. I've been interested in making stars, ocean, chrono triggers type of RPG. Any idea of what your next project might be? We're still working on the Birdie Rose Close, kind of combining the web scraper into more of a full stack now. So I'm thinking like we can either go two ways. We can start to build the web page, or we can kind of build more of a database to sync everything up together. Mike, where's the stock hub version? Yeah. I think Ray, he asked me if you have any intention of learning C++ or C ever. I think I do have some, actually, I do have some real interest in learning C, and going down that rabbit hole. I would like to pick up like a C book and read it like in my free time, probably like off stream. Um, yeah, so I do have some interest in learning C down the road because I do want to write some programs that are a little bit faster. Maybe that like, incorporate with like drivers and actually hardware, like audio-based programs. Maybe make my own like amp simulators, like vintage amps, like a Fender, like a tube amp, or like things like that. I think would be pretty cool. If you guys are enjoying the stream so far, feel free if you guys wouldn't mind to throw it a like. Boom. We are also if you guys aren't subscribed, you guys can subscribe. And we stream almost every single day as I teach myself computer science and programming by reading books like Introduction to Algorithms you see here, MIT 6.0002, or OpenCourseWare from MIT, Harvard CS50, and various other resources. I have a Discord link down below in the description where you can get access to all of my resources from every note I've taken, book I've read, course I've done, all in there for free for you guys. So feel free to check that out. It's a great place to be here. So let's go back through really quickly and just get some notes here. So recursion tree. In a recursion tree, each node represents the cost of a single subproblem somewhere in the set of recursion invocations. You typically sum the cost at each level to obtain the cost per level, and then you sum all the per level costs to obtain the total. I like that. I'm going to take that guy right there. Make a little sub note here. Okay. So I'm going to take this example here. We're going to paste that here. And then I'm also going to come down here. I'm going to take this recursion tree here. Paste that here. Three base cases. So these are here. I'm going to take this guy here. Like so. Okay. And here's the second example. Okay, cool. So we'll come back through, once I finish chapter 4, I'm planning on going back through and completing the exercises and in-text problems for the previous 4 chapters. So make sure you guys, be on the lookout for that. Those will be within the, I did chapter 1 live, um, but I decided to, you know, skip over them as we're reading them here, just so I can keep it kind of fluent in the videos and stuff. It's easier for me to edit. It's very difficult to go back through and chop these up with all the stutters I do, and then also if I start adding the problems as well. So I figured that I'll just go back through every so often, and once I kind of get a chunk of information, go back through and try to practice over the course, maybe like every 3 or 4 chapters or so. So cool. All right, let's keep on rolling here. 4.5. We're going to read 4.5, and that's probably where we'll call it for the study session. So the master method for solving recurrences. Okay. The master method for solving recurrences. The master method provides a cookbook method for solving algorithmic. The master method provides a cookbook method for solving algorithmic recurrences of the form of t of n equals to a times t of n over b plus f of n, where a is greater than 0 and b is greater than 1 are constants. We call f of n a driving function, and we call a recurrence of this general form a master recurrence. To use the master method, you need to memorize 3 cases, and then you'll be able to solve any master recurrences quite easily. A master recurrence describes the running time of a divide and conquer algorithm that divides a problem of size n into a subproblems, each of size n over b, which is less than n. The algorithm solves the a subproblems recursively, each in t of n over b time. The driving function, f of n, encompasses the cost of dividing the subproblem before the recursion, as well as the cost of combining the results of the recursive solutions to subproblems. For example, the recursion arising from Strasson's algorithm is a master recurrence with a equals to 7 and b equals to 2. A driving function, f of n, equals to big theta n squared. As we have mentioned in solving recurrences that describe the running time of an algorithm, one technicality that we'd often prefer to ignore is the requirement that the input size n be an integer. For example, we saw that the running time of merge sort can be described by recurrence 2.3, t of n equal to 2t of n over 2 plus theta n on page 41. But if n is an odd number, we really don't have 2 problems of the exact half of the size. Rather, to ensure that the problem sizes are integers, we round one subproblem down to the floor of n over 2 and the other up to the size ceiling of n over 2. So the true recurrence is theta n equal to, so the true recurrence is t of n equals to t of the ceiling n over 2 plus t of the floor n over 2 plus theta n. But this floor and ceilings recurrence is longer to write and messier to deal with than recurrence 2.3, which is defined on the reals. We'd rather not worry about floors and ceilings if we don't have to, especially since the 2 recurrences have the same big theta n log n solutions. The master method allows you to state a master recurrence without floors and ceilings implicitly infer them. The master method allows you to state a master recurrence without floors and ceilings and implicitly infer them. No matter how the arguments are rounded up or down to the nearest integer, the asymptotic bounds that it provides remain the same. Moreover, as we'll see in section 4.6, if you define your master recurrence on the reals without implicit floors and ceilings, the asymptotic bounds still don't change. Thus, you can ignore floors and ceilings for master recurrences. Section 4.7 gives sufficient conditions for ignoring floors and ceilings in more general divide and conquer recurrences. So the master theorem. The master method depends upon the following theorem. Theorem 4.1, master theorem. Let a be greater than 0 and b greater and b, let a be greater than 0 and b greater than 1 be constants, and let f of n be a driving function that is defined and non-negative for all sufficiently large reals. Define the recurrence t of n on n which is in the values of n. Okay. By t of n equals to a t of n over b plus f of n, where a times t of n over b actually means that a prime t of the floor of n over b plus a double prime t of the ceiling of n over b for some constants a prime which is greater than 0 and a double prime which is greater than or equal to 0, satisfying the a equals to a prime plus a double prime. Then the asymptotic behavior of t of n can be characterized as follows. 1. If there exists a constant that is greater than 0 such that f of n is big O of n to the power of log base b a minus said constant, then t of n equals to big theta n to the power of log base b times a. If there exists a constant k greater than or equal to 0 such that f of n is equal to big theta n to the power of log base b times a times log to the power of k times n, then t of n is equal to big theta n to the power of log base b times a times log to the power of k plus 1 times n. If there exists a constant that is greater than 0 such that f of n is equal to big omega of n to the power of log base b times a plus said constant, and if f of n additionally satisfies the regularity condition a times f of n over b, which is less than the constant c times f of n for some constant c less than 1 and all sufficiently large n, then t of n is equal to big theta f of n. Before applying the master theorem to some examples, let's spend a few moments to understand broadly what it says. The function n to the power of log base b times a is called the watershed function. In each of the three cases, we compare the driving function f of n to the watershed function n to the power of log base b times a. Intuitively, if the watershed function grows asymptotically faster than the driving function, then case 1 applies. Case 2 applies if the two functions grow at nearly the same asymptotic rate. Case 3 is the opposite of the case 1, where the driving function grows asymptotically faster than the watershed function, but the technical details matter. In case 1, not only must the watershed function grow asymptotically faster than the driving function, it must grow polynomially faster. That is, the watershed function n to the power of log base b times a must be asymptotically larger than the driving function f of n by at least a factor of big theta to the power of that constant. For some constant, epsilon that is greater than e. Is that epsilon? I don't know. I can't remember. The master theorem then says that the solution of t of n, which is equal to theta of n log to the power of, the master theorem then says that the solution is t of n, which is equal to big theta n to the power of log base b times a. In this case, if we look at the recursion tree for recurrence, the cost per level grows at least geometrically from the root to leaves, and the total cost of leaves dominates the total cost of the internal nodes. In case 2, the watershed and driving functions grow at nearly the same asymptotic rate, but more specifically, the driving function grows faster than the watershed function by a factor of big theta of log to the power of k times n, where k is greater than or equal to 0. The master theorem says that we take on an extra log n factor of f of n, yielding the solution t of n equals to big theta n to the power of log base b of a times log to the power of k plus 1 times n. In this case, each level of the recursion tree costs approximately the same, big theta n to the power of log base b times a times log to the power of k times n, and there are big theta log n levels. In practice, the most common situation for case 2 occurs when k is equal to 0, in which case the watershed and driving functions have the same asymptotic growth, and the solution is t of n equals to big theta n to the power of log base b times a times log n. Case 3 mirrors case 1. Not only the driving function grows asymptotically faster than the watershed function, but it grows polynomially faster. That is, the driving function, f of n, must be asymptotically larger than the watershed function by n to the power of log base b times a, by a factor of n to the power of n, by a factor of big theta n to the power of e for some constant e greater than 0. Moreover, the driving function must satisfy the regularity condition that a times the f of n over b, which is less than c times f of n. This condition is satisfied by most of the polynomial bounded functions that you are likely to encounter when applying case 3. The regularity condition might not be satisfied if the driving function grows slowly in local areas, yet relatively quick overall. Exercise 4.5 through 5 give an example of such functions. For case 3, the master theorem says that the solution is t of n equals to big theta of f of n. If we look at the recursion tree, the cost per level drops at least geometrically from the root to the leaves, and the root costs dominate the cost of all other nodes. It's worth looking again at the requirement that there be polynomial separation between the watershed function and the driving function in either case 1 or case 3 to apply. The separation does not need be much, but it must be there, and it must grow polynomially. For example, for the recurrence of t of n equals to 4 of t of n over 2 plus n to the power of 1.99, admittedly not a recurrence you're likely to see when analyzing an algorithm, the watershed function is n to the power of log base b times a, which is equal to n to the power of 2. Hence, the driving function, f of n equals to n 1.99, is polynomially smaller than the factor of n to the power of 0.01. Thus, case 1 applies with a constant value of 0.01. Interesting. Okay, so I'm going to quickly just take this, get some more information on this watershed function. So let's take this master theorem portion here. Let's go here. Let's throw it here. Let's say break down, please. Okay. Master theorem, which is one of the most important results in divide and conquer analysis, is giving you a shortcut to solve the recurrences of the form of t of n is equal to a of t of n over b plus f of n, without always drawing recursion trees or doing substitution. Let's break it down step by step. What the pieces mean. A is how many subproblems each level produces, and b is how much smaller each subproblem is, and f of n is the driving function, which equals the cost of work outside the recursive calls. N to the power of log base b of a is the watershed function, a baseline growth from just the recursive structure. So the key is to compare f of n to the watershed function. Okay, so we have So theorem 4.1, the master theorem. So it states, let a be greater than 0 and b greater than 1. Be constants, and let f of n be a driving function that is defined and non-negative on all sufficiently large reals. Define the recurrence given. Okay. So we have this, right? Which is the kind of master theorem template for a recurrence. What it actually means, right? The two problems divided together to make this. The two subproblems, right? Together to make this. Depending on if you have odd or even n. So then let's say this is a formal statement of the master theorem. I'm going to break it down slowly. We're analyzing the recurrence of the form of this, where we have these rules. The watershed function. The key term is this. So we have some watershed function, which is this guy here. Which is n to the power of log, how can I do this? Let me see if I can. Is there a place here that has the watershed function listed out for me? I can screenshot it. Let's do it like this. Okay. It's kind of small, but the watershed function. Okay. So what does the watershed function actually tell us? In each of the three cases, we compare the function of event to the watershed function. Intuitively, if the watershed function grows asymptotically faster than the driving function, then case 1 applies. So we'll say if the watershed function grows asymptotically faster than the driving function, then case 1 applies. Case 2 applies if the two functions grow at nearly the same rate, asymptotic rate. And then case 3 applies when the driving function grows asymptotically faster than the watershed function. Okay, so these are the cases. So let me take a screenshot then of these cases. Sweet. Okay, so then what does this mean then? The watershed function, this represents the cost of all recursive subcalls together. Okay, so the watershed function, right, represents the cost of all recursive subcalls together. Okay, right? Let's say case 1 applies if the watershed function corresponds to the driving function. Okay. So the three cases. Case 1, the driving function is smaller if, right, if the watershed function for the recursion work dominates, the result is the watershed function. Example, where you have a recursion of this and a watershed function of n cubed, and it grows slower than the watershed function. So case 2, they're about the same size. So if our watershed function is here, so if our watershed function, a big theta is n log to the base b times a, we're about the same size. The result is this. So example is here, and we have a watershed function which is equal to n, right? This is also bounded by n. N log n. Oh, so this is just kind of like, showing you the math behind how we get some of these typical, like how we can derive some of these typical running times n log n, using these like master theorem properties for recurrences, kind of like as templates, right? So we can derive running times of each of the recursive steps and then sum them up as a whole. And then this master method just provides a way to do that given three distinct cases of this kind of watershed function compared to the driving function. Whereas before we were solving with substitution or a recursive tree. So what's this teaching us? The master theorem is teaching you how to quickly classify recurrences by comparing two functions, the recursion cost and the non-recursion cost. Depending on which grows faster, you pick which case. I'm going to take this. I like this. Right, let's do that there. So this is the power of Hey, thank you for the follow. Chino, I appreciate you so much for following on Twitch. Thank you so much, my guy. Thanks for following us on here. Let's go here. Hold on. So let me grab this watershed function image. Put this here, the recursion cost, which is the watershed function, and then which is f of n. Cool. Okay, almost there. Let's get caught up in some chats here. Hey, Ray, have you ever intention? Oh, yeah, I answered that one. Chadia, have you graduated? Yeah, I graduated back in 2021 with a degree in human biology and a minor in chemistry, and I've been teaching myself computer science and programming just in my spare time here after my 9 to 5 job as a formulation chemist. So if you guys are interested in, having self-taught computer science and mathematics, consider following along and subscribing to the channel as I strive, and my goal is to do it every single day. So thank you guys so much for being here. And yeah, and this channel is just kind of a documentation of the entire process, kind of like a video journal series, and yeah, I guess. I don't know. Okay. Using the master method. To use the master method, you determine which case, if any, of the master theorem applies and write down the answer. As a first example, consider this recurrence. For this recurrence, we have a equal to 9 and b equal to 3, which implies that the watershed function is big theta of n squared. Since f of n is equal to big O of n to the power of 2 minus some constant for any constant less than or equal to 1, we can apply case 1 of the master theorem to conclude that the solution is t of n equals to big theta n squared. That was a lot easier than before, right? Now consider the recurrence this, which has a equals to 1 and b equals to 3 over 2, which means that the watershed function is equal to n to the power of 0, which is 1. Case 2 applies since f of n is equal to 1, and which equals to big theta is equal to 1. These are big theta of 1. Case 2 applies since f of n is equal to 1, which equals to big theta n to the power of log base b times a times log to the power of 0 times n, which is equal to big theta of 1. The solution to the recurrence is t of n equals to big theta log n. For the recurrence of t of n equals to 3 times t n over 4 plus n log n, we have a equals to 3 and b over 4, which means that the watershed function is big O of n to the power of 0.793. Since f of n is equal to n log n, and big omega equals to n log base 4 of 3 plus some constant, where some constant can be as large as approximately 0.2, case 3 applies as long as the regularity condition holds for f of n. It does because for sufficiently large n, we have that a times f of n over b is equal to 3 n over 4 log n over 4, which is less than 3 over 4 times n log n, which is equal to c times f of n for some constant c, which is equal to 3 over 4. By case 3, the solution to the recurrence is t of n, which is equal to big theta n log n. Now let's look at this recurrence, where 2 times t of n over 2 plus n log n, where we have a equals to 2 and b equals to 2, a watershed function equals to n, and case 2 applies. Since f of n is equal to n log n, big theta of the watershed function equals to the log to the power of 1 times n. We conclude that the solution is big theta n log squared times n. We can use the master method to solve the recurrences we saw in sections 2.3.2, 4.1, and 4.2. Recurrence 2.3, which is this, on page 41, characterizes the running time of merged sort. Since a is 2 and b is 2, the watershed function is n. Case 2 applies because f of n is equal to big theta of n, and the solution is t of n equals to big theta n log n. The recurrence 4.9, t of n is equal to this, on page 84, describes the running time of the simple recursive algorithm for matrix multiplication. We have a equals to 8 and b equals to 2, which means that the watershed function is n to the power of log b of a, which is equal to n cubed. Since n cubed is polynomially larger than the driving function, f of n, which is equal to big theta of 1, indeed we have f of n equals to big O of n to the power of 3 minus some constant for any positive constant less than 3, case 1 applies. We conclude that t of n is equal to big theta n cubed. Finally, recurrence 4.10, t of n equals to 7t of n over 2 plus big theta n squared, on page 87, arose from the analysis of Strasson's algorithm for the matrix multiplication. For this recurrence, we have a equals to 7 and b equals to 2, and the watershed function is n to the power of log b a, which is equal to n to the power of log 7. observing that log 7 equals to 2.8, we can let e equal to 0.8 and the bound of the driving function be f of n equals to big theta n squared, which is equal to big O, which is equal to big O n to the power of log 7 minus e. Case 1 applies with the solution of t of n equals to big theta n log. Case 1 applies with the solution t of n equals to big theta n to the power of log 7. Okay, so let's just take these. I'm going to say, I get that this is showing me some examples of how to use the master method. I am a little confused on when case 1 applies and they get this E constant. Great question. The mysterious epsilon is a part of the, it probably usually trips people up at first. Let's go over each step. In the case 1 says that for some constant epsilon greater than 0, right, then this. Okay, so that's what case 1 explicitly says. So case 1, oh yeah, so A minus epsilon. Oh, so it's just a property of the actual case. So then how did they get 0.8 from this? Because they do A minus the epsilon. So log base 7 minus epsilon, we can let epsilon equal 0.8, which is greater than 0 but less than 1. I'll take this, so let me see. So A equals to 8, B equals to 2. The watershed comes out to n cubed. So f of n is just big theta of 1, just constant work outside recursion. Now check case 1 condition. So for some epsilon greater than 0, is theta of 1 smaller than n cubed polynomial? Yes, it's way smaller. In fact, 1 is equal to big O of n to the power of 3 minus that epsilon for any epsilon which is in between these bounds. This case applies. So example 2 in Strassen, so here we go, 7 and 2, n squared. Now let's compare to n squared to n to the power of 2.807, right? Is n squared equal to this for some constant? Okay, so they just choose 0.8 to make it equal about, to tailor it to case 2, or case 1. Oh, okay, got you. Yes, if you have to pick a epsilon value there, but doing so makes them about the same. So case 2 apply, no? That's exactly where people get tripped up. Case 1, f of n is polynomially smaller than the watershed. Case 2, f of n is about the same order as the watershed. And case 3, f of n is polynomially larger than the watershed and passes the regularity check. If you can find some epsilon greater than 0 such that right, this is true, then it's case 1. They differ only by a factor, a log factor. So in Strassen's case here, the exponent gap is about this. So yes, for some epsilon, so you pick. Oh, so there is some sort of there is like a exponential gap between the values. There's a distinct polynomial gap, so case 1 applies. Could we prove that there is this gap of 0.8 in the exponent? So we proved that there is a difference in the exponent of a value of about 0.8, showing that case 1 then applies for the watershed function being polynomially larger than the f of n. Of any epsilon greater than 0. Interesting. Cool. Yeah, it might be overkill, but who cares? We're learning, we're having fun. We'll just know more than the next guy. That's how I view it. Cool. When the master method doesn't apply, there are situations where you can't use the master theorem. For example, it can be that the watershed function and the driving function cannot be asymptotically compared. We might have that the f of n is, what does this mean? Is it going to be able to do it? So it's f of n okay, there we go. Yeah, this is case 3 of the master theorem. It means that what does the mean? Much greater than or much less than. Okay. That would make sense. Okay, we might have that f of n is much greater than the watershed function for an infinite number of values of n, but also that f of n is much less than the watershed function for an different number of values of n. As a practical matter, however, most of the driving functions that arise in the study of algorithms can be meaningfully compared with the watershed function. If you encounter a master recurrence for which that's not the case, you'll have to resort to the substitution or other methods. Even when the relative growths of the driving and watershed functions can be compared, the master theorem does not cover all the possibilities. There is a gap between cases 1 and 2 when f of n is equal to little o of the watershed function. Yet the watershed function does not grow polynomially faster than the driving function. Similarly, there is a gap between cases 2 and 3 when f of n is equal to little omega of the watershed function and the driving function grows more than polylogarithmically faster than the watershed function, but it does not grow polynomially faster. If the driving function falls into one of these gaps, or if the irregularity condition in case 3 fails to hold, you'll need to use something other than the master method to solve the recurrence. As an example of a driving function falling into a gap, consider the recurrence t of n equals to 2t of n over 2 plus n over log n. Since a is equal to 2 and b equals to 2, the watershed function is equal to this, which reduces down to n. The driving function is n over log n, which is little o of n, which means that it grows asymptotically more slowly than the watershed function of n. But n over log n grows only logarithmically slower than n, not polynomially slower. More precisely, equation 3.24 on page 67 says that log n is equal to little o of n to the power of some constant for any constant epsilon greater than 0, which means that 1 over log n is equal to little omega of n to the power of epsilon, and n over log n is equal to little omega of n to the power of 1 minus epsilon, which equals to little omega of the epsilon which is equal to little omega of n to the power of log base b of a minus epsilon. Thus, no constant epsilon greater than 0 exists such that n over log n equals to big O of n to the power of log base b of a minus epsilon, which is required for case 1 to apply. Case 2 fails to apply as well, since n over log n is equal to big theta of n to the power of log base b of a times log to the power of k times n, where k is equal to -1, but k must be non-negative for case 2 to apply. To solve this kind of recurrence, you must use another method, such as the substitution method, section 4.3, or the Acrobasi method in section 4.7. Exercise 4.6-3 asks you to show that the answer is big theta of n log n. Although the master theorem doesn't handle this particular recurrence, it does handle the overwhelming majority of recurrences that tend to arise in practice. Cool, and then we have some exercises here to solve. So 4.6 starts on page 107 and goes until (115), about 8 pages. Cool, so that's where we will pause for today. There in 4.4 and 4.5. So we read the recursion tree method for solving recurrences and 4.5, the master method for solving recurrences. These are just basically trying to figure out ways to sum up and come up with a running time for an overall function by finding the running times of its individual recurrences and summing those together to find the overall running time of the problem at hand. Now, we can do this by using a recursion tree method for finding, the kind of like the bottleneck of the overall, function, which is, you could break down into certain subproblems within each recursive step, and then those subproblems are broken down by a factor, and then the actual subproblems are, created by a certain factor as well. Then we have a master method, which basically has this watershed function where you take this watershed function and apply certain comparisons to your function at hand. And then if certain cases apply, you can then use this master method to make some generalizations fairly quickly about the overall running time of the algorithm. So let's go ahead and just do a quick. All right, so I want to do a quick review over what I went over today. So I read 4.4, the recursion tree method for solving recurrences, which basically talked about how we can draw recursion trees to visually show the running times of recursive algorithms, where you have some sort of root, or recurrence time that it takes for the root action to take, as well as for the summing of all of the individual recurrence substeps. Now, these recurrence substeps are reduced by a certain factor and then also multiplied by a various factor based on how many children are coming off of each parent. We can then sum up all of these substeps to come up with an overall running time of the algorithm. Now, there are some cases where the individual substeps or even the leaf node steps may override or have more weight than that initial root timing to get the algorithm started. So it really is dependent upon the actual type of problem for where within these 3 steps, whether at the root, within the internal nodes, or at the leaves, is the kind of driving factor of the recurring time, for lack of better words. That's a solid summary. Recap of recursion tree method. What it is: a visual tool for analyzing the running time of recursive algorithms. You draw a tree for each node represents a subproblem. The root corresponds to the original problem, and children nodes correspond to recursive calls, usually smaller in size. The subproblem properties. Each node has a cost at that node, work done outside of the recursion, and a size reduction factor, and a multiplicity factor. summing up the cost. The total running time is the sum up of the cost of all the nodes in the tree, right? The dominant cost can come from the root, the internal nodes, or the leaf nodes. Insights. By analyzing how costs shrink or multiply at each level, we can identify which level dominates the total runtime. Often the pattern of growth at each level gives intuition for the master theorem cases. Why is this helpful? I like this a lot. I'm going to say, can you rewrite this? Can you write this in Markdown format? I'm going to copy that. Let's go here. Paste this here. Actually, I'm going to say don't use title hashes, just bullets. Cool. I like that a lot. That'll be good for our notes for kind of like a general summary. I think that we should do that more often at the end of our individual sections to kind of have a general summary. That's a smart, I think. So what I'll do here is I will say this is I will do here, I'll say, I'll do a double. .4 quick review. Yeah, that looks good. I like that. Okay. Okay. Now let's go here and say, now in section 4.5, the master method for solving recurrences, we were given a more catch-all general use case for quickly identifying running times of recurrences based on a watershed function and analyzing this and comparing it across or against our original function. Now we are given three cases where one is asymptotically faster, asymptotically slower, and then about the same. And in each case, we have various conditions that kind of infer certain running times. Can you provide a similar summary as you did before, but for this one? Well, this one's a little bit more tricky. Hey, what's going on, Ray? Welcome in, my guy. How's you been learning? So the master method, section 4, quick review. What it is, in general, a technique for solving recurrences of the form this. Okay, so let's take this and let's say so master method, quick review. Oh, hold on. So actually, I think I need to do 3. Yeah, 3. There we go. Now that makes a nice little subheading. Okay, so what is it? In general, a general technique for solving recurrences of the form. already have this picture. Where are you at? Here, up at 4.5. Here. Okay. A general technique for solving recurrences of the form t of n is equal to a times Tn of w plus f of n, where a is greater than 0, b is greater than 1, f of n is equal to the work done outside the recurrence. Quickly identifies the running time for without fully expanding the recursion trees. Uses the watershed function. So the watershed function is this guy. Uses the watershed function. Representing the work for recursion itself. So we already have the three cases above. So I'm going to remove this. So intuition, comparing the driving function to the watershed function. Which is this guy. Cool. That looks good. All right, sweet. That looks really good. How's everybody doing? Welcome in, everybody. Welcome, welcome, welcome. All right. Does that look good? Quick recap. 4.5. Quick review. Okay. Yeah, that looks good. Let me delete this. Okay, so we completed section 4.4 and 4.5 today. So just a quick recap. Section 4.4, we talked about recursion tree method, which is a visual tool for analyzing the running time of recursive algorithms. We draw a tree for each node, represents a subproblem. The root corresponds to the original problem, and children nodes correspond to recursive calls, usually smaller in size. Subproblem properties are the cost of each node, which is work outside the recursion, which is f of n, the reduction factor, and the multiplicity factor. We sum up the costs, right? Or what is it saying here? T goes to cost at root. So really quickly, let me edit that. T of n equals sum of cost of the tree, which is T of n equals to cost of the root plus sum of the internal nodes plus sum of the leaves. Yeah, that looks good. All right, let's go ahead and push this up. All right. Sweet. If you guys would like access to these notes, they are found in my on my GitHub repo live in my description or in my Discord as well. So feel free to check those out if you are wanting to get access to kind of these notes and kind of get a really good overview of what the chapter was about. And yeah. So thank you guys so much for being here and hanging out with me for this hour and 45 minutes study session we did today, where we read chapter 4 from Introduction to Algorithms by CLRS. We read section 4.4 and 4.5 on recurrence, solving recurrences and timing complexity of recurrences using recurrence trees and the master method. So thank you guys so much for being here today. I'll probably jump back on a little bit later this evening for an actual coding session, either working on MIT OpenCourseWare 6.0002 Introductions to Computational Thinking and Data Science Problem Set 3, or I will be working on our project, which is building the Birdie Roast Close web page web scraper combination. So thank you guys so much for being here, and I'll see you guys a little bit later this evening potentially, but for sure tomorrow for a longer stream. I'll be free to stream tomorrow for quite a while, so probably have a good 3 or 4 or 5 hour stream tomorrow, as well as probably play some Counter-Strike to end the week off on a good note. So thank you guys so much for being here, and I'll see you guys a little bit later this evening potentially for a little bit more of a coding session. But this was a good little study session. I learned a lot. It was very dense, but it was really helpful to break down the information with ChatGPT and get some more notes here to better understand recurrences and time complexity, because this was a lot of information. But I feel a lot better now that we kind of broke down the notes for sure. So let me know how you guys are feeling regarding recurrences and the book so far. I've got a lot of positive feedback regarding the chopped up versions on the YouTube, which are basically just like an audiobook where I kind of get rid of all of the stutters and errors and chat reads and typing and whatnot, and it's just straight reading. So if you guys would like to go back through and listen to those kind of as an audiobook, it's a great way to get the content quickly. So thank you guys so much for being here, and I'll see you guys a little later. Thank you guys. Bye.